Hello everyone, I'm Taihao from Missouri ST. Today I'm going to give the presentation about the towards smart and sustainable cement manufacture process, analyze and optimization of cement clinker quality using thermodynamic and data-informed approach. So I think in this room we all love concrete. We know the concrete is a major materials used for the infrastructures, but we also need to face one issue about concrete, the carbon emission. So the cement manufacturer contribute to the 8% of carbon emission globally every year, and then that is a big issue. And it's really hard for cement sector to reduce carbon emission because the carbon emission from the coal reaction for the clinker process, the decarbonation of the limestone and the form the ALAT because you need to use your burning your fossil fuel to heat everything above 1450 degrees to get a lot of ALAT here. So due to the restrictive government policy, also it's very expensive to buy the carbon credit. So cement manufacturers start to take some action to adopt the sustainable manufacture process. I'm going to give you some examples that they have taken here. So first, they have tried to use carbon capture equipment to add additional equipment that can capture all the gas released from the manufacture process, and then they separate the other gas with carbon dioxide, and then store the carbon dioxide for other use. So that is good, but you need invest a lot of money to get equipment to install it and operate it. Also, you need additional land to store your carbon dioxide. So that is not available for all the cement plants. It's only few cement plants adopt that technique. Another way they use supplementary cementitious material to partially replace clinkers in the cement. So that means you use less clinker, you produce less clinker that reduce carbon emission. So I think in the US, all the Portland cement is now replaced by the 10% limestone right now. But also cement manufacturers want to increase the replacement level, but it's hard because limestone is an inert material. Basically, if you have higher replacement level, you will compromise your performance. And also, they are trying to use some material that have polyolanic reaction, something like fly ash, slag. So basically, if you have polyolanic reaction, you can have higher replacement level, but do not compromise, do not sacrifice your performance that much. But there's one issue for the fly ash or slag that kind of industry waste. So you can expect their chemical composition, they're different. So and we know the chemical composition from this kind of material can significantly affect your performance of your concrete. So that means you cannot get a consistent quality product. That is also unacceptable for the commercial product. So in that way, we still have a lot of research need to going on to get a consistent property product. Another way they are doing is to significantly change the way they produce the manufacture cement. So this technique is still under lab development. So basically, in this technique, they extract the calcium from from calcium rich materials, not limestone like fly ash. Use some wet chemistry and some ultrasonic technique, and then you adjust pH. You can get calcium hydroxide. Use calcium oxide in your manufacture process. In that process, you do not need to deal with the carbonation of your limestone. So that can significantly reduce your carbon footprint. But there's still some challenge in this technique. So when you extract the calcium ions, you also extract other ions. But we don't want the other ions in your cement manufacture process because it can cause some bad issues. You basically can get low quality cement clinker. So what should we do? So as I talked there are a lot of techniques they have taken, and still some, since it's still on the lab scale, it's a long way to go to the to go the industry scale. Also, you cannot get consistent quality of your product. So what we should do? So we want something low cost, and we can use immediately. So that we introduce the smart manufacturing process. Basically, you use AI platform to optimize your entire manufacturing process. In that way, you can enhance your production efficiency and reduce your energy consumptions. So there's one study have shown that in the cement manufacturer, people start to use smart cement manufacture. For the traditional method, basically you characterize your raw materials, and you based on the equivalence and some metrics like Lamb spectral factor to determine your manufacturing process, and then you characterize your final product. If you get a low quality product, you can do nothing with that. You need to accept that. But for the smart manufacturer, it has a sensor at each step, and the AI platform receives the sensor data from each step, and then it can optimize the entire process parameters. Like, for example, if the previous temperature is lower than X, it may increase the temperature for the next step, something like that. But this study show here is you still need some customized sensors, and also you need, after you install your sensor, you need a long time to collect data to train your AI platform, because there's still some difference between the cement plant to plant. So you can use the data from other plants, but still you may not get accurate prediction or accurate optimization here. Also, this study only focus on the optimize the processing parameter, not focus on the raw material optimization. Because if we know we have a good quality raw materials, we may use a lower temperature to produce high quality cement. So in our studies, we are going to develop AI platform that can optimize, that predict your cement qualities based on your raw material ratio, also your processing parameters. So to achieve that, first we use thermodynamic simulation to predict thousands of like cement clinker phases here. I mean, somebody may ask, okay, why don't you directly use thermodynamic simulations instead of machine learning? So because we already know thermodynamic simulation is reliable, a tool to use. To answer that, first, if a cement plant want to use thermodynamic simulations, they need an expert knowing the thermodynamic, knowing the material science. So it's a high labor cost, but for machine learning, you just need type in some numbers, click go buttons, and I think most of people with high school diploma can do it. So it significantly lowers the labor cost. But the most important thing, the thermodynamic simulation cannot do the reverse engineering. So thermodynamic simulation can, if you give the chemical composition of your raw materials, it can tell you the phase, your phase composition of your clinker. But if you have target phase composition of clinker, the thermodynamic cannot tell you how much calcium you should use in your raw materials. So, but machine learning can do that in reverse engineering to help you to optimize your composition of your raw materials. Other than that, we're also going to, based on those results, we are also going to refine the range of Lamb spectral factor, so that can help cement manufacturers produce high quality clinker. So first, this is the results from the thermodynamic simulations. So we use FactSage to perform the thermodynamic simulations, and the input basically use the chemical composition, different processing temperature, pressures. We predict the phase composition at different temperatures, 1500, 1450, until 1250s. So basically from here we can see, from this figure we can see if you have a crack composition of your raw materials, you can form a lot of ALAT at basically around 1300 degrees. So that is significantly lower than the temperature most manufacturers use right now. Also, we compare our thermodynamic simulation results with XRD analysis with different literature, and they get good match here. So we believe our thermodynamic simulations are reliable. Next, we run the thermodynamic simulations, and we want to use that result to refine the Lamb sector factors. So Lamb sector factor, a lot of manufacturers use that to evaluate their clinker qualities. And then on the market, for Portland cement, the Lamb sector factors range from 75 to 99. It's a large range. And in that range, you can still expect a lot of low-quality clinkers. So in that way, we want to narrow that range to give you a range that can definitely produce high-quality clinker. So we plot the C3 acids against LS factor. Also, we plot the C2 acids against LS factor. So if you want a very high-quality type 1 cement, that you should have 89 to 96. Also, if you want produce some billet enriched cement, like something like type 4, you should your Lamb sector factor to from 59 to 71. So that is first study to show the Lamb sector factor for the billet enriched cement. After we develop that, we are going to use machine learning to develop our AI platform. So as many previous speakers talked, so machine learning, basically you find the machine learning model can find input-output correlation from the training data set, and then you apply a new testing data set. The machine learning can give you the property of your materials. So in our studies, we use the training database obtained from the thermodynamic simulation. It contains more than 1,000 cement clinker systems here, and the chemical composition, temperatures are used as input variables here, and the output basically the phase composition of the cement. And for the testing, we also generate from thermodynamic simulation that composition not has been used in the training data set. It includes like 200 clinker system in the testing data set. So here is our machine learning results. So you can see we have predict the phase composition like C3S, C2S, C3A, and C4AF for heating and cooling process. And then the dashed line means the ideal predictions, and the solid line is like 10% error bound. So basically most predictions fall between that 10% error bound. So we think it's reliable predictions. And still compared to the thermodynamic simulations or other methods, so basically you don't need to fine-tune your parameter by yourself. You can automatically do everything, and that can avoid a human error. Also, based on the result, I think we can use our AI platform for smart cement manufacturers that can minimize infrastructure costs. So basically, you do not need to add additional equipment to your cement plant. Also, that can optimize your clinker qualities here. Except then that, after we develop our AI platform, we also want to optimize the raw material domain to produce high-quality cement. So this figure is usually used by cement manufacturer to produce to find the crack ratio to produce high-quality clinkers. And I mean that is a good figures, but if you want to use these figures, you need to heat everything above 1450. But we already know if we have good quality raw materials, you can produce high quality cement clinker at 1300 degrees. So basically, we run multiple prediction from our AI platform, so we get that. So that is the chemical composition we should use for 1300, 1350 to get high quality clinkers here. So if you want to use 1300 degrees, you need to make sure your raw material, the molar ratio of calcium to silica is more than 3. So in that way, you can definitely to produce your high quality clinkers at 1300 degrees. But if you do not have that high quality raw materials, you want to use 1450s, you have much larger range you can use compared to the previous figure I show here. So basically, you only need to make sure your molar ratio of calcium to silica is more than 1.6, that you can produce high quality clinker at 1450 degree. Next, I want to talk about optimization. So as I said before, for the machine learning, if you have a target phase compositions, machine learning can help you optimize the chemical composition of your raw materials. Here we have target C3S composition, and then we want to optimize the calcium silica ratio here. So basically, the red line, the blue line is from our AI platform itself, the optimization from our AI platform, and the red dot is from thermodynamic simulations. So we can see they have a good match, but there is one issue here. You can see each chemical compositions may have like 2 target C3S. We know that it's impossible for realities. So that's the reason we didn't constrain our models. So in the future study, we will constrain our models based on the alumina and iron content, because we know that if we have high alumina and iron content, basically we form 4C3A and C4AF, so that we cannot have that like C3S above, like beyond 40, something like that. Overall, I think machine learning is a powerful tool especially for the smart manufacturers. We can predict the quality of the clinker. We also can optimize the raw material ratio. Use the machine learning, we can discover the optimal domain for the raw material composition that can produce high quality clinkers. Also, smart manufacture is a very promising way to enhance the efficiency of production, also the reduce the carbon emission. Yeah, that's all I have today. Thanks, guys.
Thank you.